Section 11.7, General Strategy for Testing Series. So we have a whole slew of tests for convergence and divergence in our toolboxes now, our mental toolboxes. So how do we figure out which one to apply when we're looking at an infinite series? And that's what this section is about. So this video is just going to run through just sort of some general strategy that you can apply when you come across a series, look at a couple of examples, not to go through the whole test on each of these examples, but just which test to apply for the examples. And then you'll get some practice with a quiz where you look at a variety of different infinite series and decide which test you want to apply. Very similar actually to integration, where there are sometimes multiple tests that could work to test it for convergence, but sometimes one is more efficient than, say, another test. So let's talk about some strategy here. So the first thing, when we come across a series, the first thing we want to do is we want to just either mentally, visually look at the series and look at the limit of the terms and see, do those terms approach zero as the index approaches infinity? If they don't, then we can quickly apply the divergence test and be done. So I've just copied the divergence test right here, just what is the divergence test, but basically we have to look at the limit of the terms. So let's just look at a quick example that would be sort of an obvious one that we would want to apply the divergence test to. So here would be a little example of this. Let's just say I were to come across something of the form -1 to the k squared over 2k squared plus 5 from k equals 1 to infinity. So quickly, whether I do this in my head or I actually write it out, I look at this series and I say, you know what, if I first have to take, I can't take the limit with that switch on it. So since I can't take the limit with the switch on it, what I can do is I can first start by looking at, well, what's the absolute value of the terms? And the absolute value of the terms takes off the switch, leaves me with k squared, 2k squared plus 5. And if I take the limit of that, I can see very quickly that that is two polynomials. Lots of ways to deal with that. I'm going to just say that the degree of, deal with that meaning take the limit of it, the degree of p of k equals the degree of q of k, and therefore it's going to be the ratio of the coefficients, 1 over 2. But that is clearly not equal to 0. Now that wasn't the limit of my series, that was the limit of the absolute value of my series. But what I can say now is, since the limit as k went to infinity of the absolute value of my terms in my series was equal to 1/2, with that switch, -1 to the k, the limit as k approaches infinity of just a sub k oscillates. Well, I should actually say it this way. It just doesn't exist. It doesn't have a limit because it oscillates between positive and -1/2. Therefore, this series must be diverging. The series itself, -1 to the k squared over k squared plus, 2k squared plus 5, diverges by the divergence test. Okay? And that's what we want to do. We want to do that first. If there happens to be a possibility that we diverge by the divergence test, that's the first thing we always want to do when we come across a series. So even though I said I wasn't going to run through all the examples, I just wanted to show that one real quick, because that's something that you should always do, whether you do this in your head, whether you just do the examination in your head, or you actually write it all the way out. You should always do that first. So run through that divergence test first. That's the first thing. A lot of times when we run through that divergence test, of course, that this is what's going to happen, right? If the limit is actually equal to 0, then the test is inconclusive. And that's going to say, okay, so now we get into our other strategies. Okay. So if it turns out that the limit is equal to 0, then we just run into our other strategies and we start working our way through. Okay, that said, The next thing we do is just examine it. Do a look at it and see, does it fit one of our special series? Is it just exactly one of our special series? Is it a p-series? Is it a geometric series? Is it a telescoping series? So remember, we even had those telescoping series at the beginning when we were first starting to discuss series. So is it one of those forms? Is it p-series, geometric, or telescoping? So just some quick examples, right? A p-series would be something of the form, if you came across 1 over n times the square root of n, from n equals 1 to infinity, right? Quick examination shows me that's 1 over n to the 3/2 from n equals 1 to infinity. And that, of course, is p-series, p equals 3/2, and that would converge. So this guy converges. All right, geometric series. What would a geometric series look like? Well, something like, let's say we had, let's write it this way. Let's say we had negative 2 to the 3k over 5 to the k, right? Again, I'm kind of just writing it. Sometimes they don't come exactly in the form, but we do a little bit of work and we get to it pretty quickly, and we can see that this is actually k equals 1 to infinity of negative 8 to the k over 5 to the k, where the ratio here is going to be negative 8/5, and therefore this guy is definitely geometric. This guy's definitely geometric, but since the absolute value of r is greater than, it's equal to 8/5, which is greater than 1, this guy is going to diverge. Okay? So this particular one diverges. All right. And then there's some examples of telescoping. So does it telescope? And if it telescopes, remember again, if it telescopes, we look for the partial sum. So if we have a telescoping series, we come up with a way to express the partial sums. So we express S sub n, okay? And then we take the limit as n approaches infinity. And we figure out if that has a limit. Okay? Okay, so those were our special series. That's what we started with when we started talking about series, and then we got into all of our different tests. So then we come across our next step. So run through the steps, right? Check the divergence test, then check to see if it's just one of our special series. Then think about this. Maybe it's not one of our special series, but maybe we could compare it to one of our special series. Maybe we could compare it to a p-series or a geometric series. And if we could compare to a p-series or a geometric series, then we can think about applying either direct comparison test, or the limit comparison test. And again, I just took these clips out of our list of all the different tests that we have. So here would be some examples of series that I would apply comparison to. Because when we come across these series, I look at these series and I think, you know what, as I approach infinity, as I look at these terms and I approach infinity, so sort of my thought process here is that this is going to behave an awful lot, this particular series is going to behave an awful lot like just k cubed over k to the 4th. And that is simply 1 over k. And so I think to myself, I'm going to compare. Whether I use limit comparison or direct comparison, that gets into kind of the details of applying the comparison test, but that's absolutely what I would do. So this is my thought bubble when I come across something like this. And the other examples I have listed here are similar. So I think about, as I come across a series and I'm trying to decide what tests to apply, if it's not exactly one of my p-series or geometric series, but it could look like that or behave like that, then I absolutely go that route. And each of these examples here does something similar, right? I think about, well, as I approach infinity, what does the numerator look like? Do some of the terms essentially get obliterated by the larger powers, or the exponentials in the last example here? I'm looking at this one and I'm thinking, well, this is going to behave an awful lot like 2 to the k over 3 to the k. This guy's going to behave an awful lot like 4n to the 4th over the square root of 3n to the 10th. And so I'm thinking about those sort of things as k approaches or n approaches infinity. All right, remember to use the comparison test, we do have to have positive terms or eventually positive terms. So if the terms themselves are positive and negative, it's worth thinking about what happens to the absolute value of the terms and look for absolute convergence with the comparison test. That's also a useful strategy to think about. Most of the time from here on out, actually, we're not going to be looking for just the difference between convergence and divergence. We're going to want to know if it converges, does it do so absolutely, or is it conditional upon a switch or positive and negative terms? Okay, so what if it doesn't look like a p-series or a geometric series? What if we can't do just a straight comparison test? Well, then we get into our root and our ratio test. So as we're examining the series, does the series, so here's just some questions to think about. Does the series have factorials in it? Does it have constants that are raised to powers with that index in the power? Are the terms themselves just in an entire expression that is raised to a power? And if any of those answers is yes, then root or ratio test is going to just have, it just has those loads of canceling for that type of series. So things to think about, right? Do you got factorials? Do you have constants raised to powers? Do you have an expression that is raised to a power? All of those are sort of clues, should we say, that a root or ratio test is useful. And so here are just some nice examples. We've got a factorial in the first one. As soon as I see that, not only do we have a factorial, but we have a factorial and an exponential, 5 to the end. So as soon as I see something like that, I'm thinking to myself, that's a great candidate for the old ratio test. This guy has, and you could, it's actually both the numerator and the denominator on that one. This next one has the entire expression is inside of a power of k. That to me is just it's like a flashing neon sign that a root test is a great option here. This next one has real similar actually to the first one with the with an exponential and an exponential with actually a switch on it, -5 to the k, and a factorial. So again, great candidate for ratio test. Okay. So those are all really good candidates for ratio test. Now, of course, the ratio test, if we run a ratio test and the limit that we're looking at comes out as 1, then it's inconclusive and we just have to try something else. So remember, if your limit as you apply the ratio or the root test comes out as 1, then your actual root test, ratio test is inconclusive and you just have to try something else, another approach. Okay? Use something else. Okay, remember that these tests themselves also test for absolute convergence. So these are testing for absolute convergence. So if we're getting out convergence here, it is absolute convergence. That is the definition of the ratio and the root test. They test for absolute convergence. Okay. When would we use alternating series test? Because alternating series test is in there too. And so this is what I would say for the alternating series test. After I've tested a series for absolute convergence using one of the methods we've discussed above, either comparison, so if the terms are have a switch on them, I would take the absolute value of them and maybe compare that way, or just run a root or ratio test. So after I've tested for absolute convergence, then if I'm getting divergence of the absolute value, then I get into the alternating series test. So that's kind of a specific time to use it, but I tend to test for absolute convergence first. So looking at the absolute convergence first, if that fails, then getting into the alternating series test, then looking at it and saying, okay, it's not converging absolutely, but does it have conditional convergence? So this is alternating series test is really good for checking for conditional convergence. So here's 2 examples. Both of these tests, both of these series, if we actually were to test their absolute value, okay, the absolute value of these series diverges. So then test with alternating series for conditional convergence. And these are just two examples. A lot of these examples I'm pulling out of previous videos or off of worksheets or homework problems. So these are just two examples actually that have showed up over time where we have applied the alternating series test and we're able to show that we had conditional convergence for these two series. Okay? So that's a great time to use the alternating series test because alternating series test doesn't tell us what type of convergence, it just says it converges. That's why I always test the absolute value first, and then you can apply the alternating series and get conditional convergence. Okay. Then when would I apply the integral test? Well, the integral test is a very specific test. So the integral test, it was a nice test at the beginning as we were building up, and it helped us to prove the p-series and so forth. But the integral test is pretty specific. You have to have an eventually continuous positive decreasing function. You have to be able to integrate that function in order to apply the integral test. So it's a pretty specific one. It works nicely if we're looking at something. This is actually, I grabbed the one that we had up above. This is nice for something like this because we can show on this particular one that the absolute value of a sub k is 1 over k ln of k, and we can use the function when we're looking at this particular series, 1 over x ln of x. We can use that function and work through this guy when we're working on the absolute value of it. So if we're looking at something like this, this would be an example of where we could use the integral test. Okay. Okay, so once we've gone through, those are our, at that point, we should hopefully have found a way to test for convergence or divergence and gotten a conclusion. But could be the case that we've run a test and our test came back inconclusive. And if that's the case, well, then we go back, we just got to try another method. It's very much like integration in that way. When we're testing series, if a process that we've used, if a test that we've used comes back inconclusive, well, then we just have to try something else. Okay. Hopefully we've gotten some clues in that process as to which way to go after that, but it could be the case that it's inconclusive and we need to try something else. Okay. All right. So that is our process. That is our strategy for testing series. So remember, it's good to be very familiar with all of our special series, especially for our p-series, our geometric series, especially good to keep those in mind for the comparisons, root, ratio, and applying our test as we go. All right. So let's get into some practice problems where you guys can apply these.